Today we're going to be talking about logistic growth. And logistic growth is a special type of growth that happens when we talk about constraints on a population. So exponential growth can be modeled by this differential equation here. As you approach a growth rate that's a maximum carrying capacity, so the most that a population can handle, you have a limiting factor that happens right here. And this is called a logistic differential equation. This equation right here is a logistic differential equation. And here you see what a logistic curve looks like. And that would be a solution curve to our differential equation. Now this is really based after an activity that we did during class. So I apologize if you found me on YouTube and you weren't there, obviously, for the activity that we had in class. But here's our differential equation. And here we're talking about a certain population of mountain goats. And we have this differential equation. And if you remember back to the previous slide, this M is the maximum carrying capacity. So when we're looking here at this one, what is the carrying capacity for the goats of the wildlife preserve? It's that number right there, 30. What is the goat population when the population is growing the fastest? Well, that's always half of the maximum carrying capacity, and that's 15. And part C, what is the rate of change? So rate of change, remember, means derivative of the goat population when it is growing the fastest. 0.008 P, which is our actual population, times by 30 minus 15. Putting that in my calculator, we get 1.8. Okay, next we have a slope field. And so this is what our slope field of a logistic differential equation looks like. It approaches something really, really high and then goes to our carrying capacity. There are 6 male and 6 female, so 6 total goats introduced. So that's like our initial value. So our initial value is down here at 6. And sketch the number of goats over time. So we increase and it almost looks exponential, but then eventually evens out to an asymptote of our 30. And I know it's really hard for you guys to see, but it's 30 there. Oh, I don't know why that disappeared. Let's redraw that in for us. Okay, now we're going to use separation of variables to solve our differential equation. And this was, or is, our differential equation. So I'm going to get these p's on one side. So we have dp is p over 30 minus p equals 0.008 dt. Now I have to integrate because they wanted me to integrate both sides. On this left side, we need to do partial fraction decomposition. I'm not going to go through that work because, quite honestly, I think I'd run out of space on this right side, or left side, I apologize, left side. But in terms of, and I haven't taken the integral yet, so that's what we get there. I'm going to pull out that 1 out of 30, 1 over 30, I apologize. and this should be a DP. I just looked at that. And I'm adding that in that 0 just so that you guys can see that this is a decimal point in there. Now I integrate, and I have ln of the absolute value of p minus the ln of 30 minus p equals 0.24t plus c. What I did is I integrated in my notes. I integrated and then I multiplied. This is supposed to be an 8. Multiplied by 30, so that's how I got that 0.24t. Now this minus sign, remember, this technically is a u substitution down here. If you need to show that work for the u substitution, show that work for the u substitution. So then this turns into this. And then writing this now as an exponential, I'm going to turn that c into a big K that's out front. I'm doing a little bit less algebra because I think I'm going to run out of space on this slide. But also, at least the students in my classroom are used to e to this piece here. You would basically be the same thing as multiplying e to the c, so we just make it some other big constant. Okay, so now I plug in 0 and 6. So when I plug in 0 and 6, I get k. I'm going to do it over here because, again, I'm a little worried about running out of room. K equals 1/4. So now I have 1/4 e to the 0.24t is equal to p over 30 minus p. Now doing a little bit of algebra. So if I multiply this 30 minus p over here, and then I isolate the two terms that have p's in them on one side, factor out the p and divide, we get p equals 30 e to the 0.24t all over 4 plus e to the 0.24t. Now to get this into maybe a little bit better of a looking form that we might see a little bit more often, we're going to multiply by e to the negative 0.24t over e to the negative 0.24t, which then gets us to this form. Eek, t plus 1. And so this, let me rewrite that so that it looks a little bit better for us. And it's in a form that our book uses. Eek, I ran out of room. So I knew I'd run out of room. Okay, so this is really important to us because any differential equation that we have, we can then manipulate it to look like this. If you remember back to this slide, 30 was our maximum carrying capacity. We have a 30 here, and that's our maximum carrying capacity. Okay, so this is the general equation when I solve my differential equation. Again, m is the carrying capacity, and k is a positive, I'm going to call it a growth constant, which that's what they're calling it. They're calling it a growth constant. Okay. Okay, now looking at another example. Let's do blue. Determine the maximum number of rabbits a field can maintain. Remember this M here, that's our maximum carrying capacity. So that's 1,000. What is the value of K? So that comes from this right here, MK. So that's that constant in front. MK, this is that constant in front. So negative 0.7 equals negative 1000K. We get K to equal I had it wrong in my notes. I had to check on my calculator real quick. It didn't look right. 0.0007. It was wrong in my notes. And then when is the population, what is the population when t equals 0? So when t equals 0, so that's just plugging into your calculator, and that's just calculator work. I'm not going to go through that, but you make t equals 0, so that makes this 1. So you have 1,000 divided by 122.51, and that is 8.163. And I'm using AP rules since they don't tell me to round to the nearest whole number. I'm rounding to 3 decimal places. Okay, next problem, or next piece to this problem, I should say. What is the population when the rate of growth is the greatest? Remember, rate of growth is the greatest. That's at half the carrying capacity. Our carrying capacity was 1,000, so that's 500. Use your calculator to determine when the population reaches that value found. So I'm basically going to set my differential equation equal to 5,000 I'm going to put this in y1, put that in y2, or y1, y2, and find their intersection. And what do I get here? I get t equals 6.857. And let's talk about some sort of time. And this is months. Okay, last example. Again, giving us our differential equation. I actually kind of really like this one. At what rate is the number of moose in a new section of a game preserved changing when I'm given that differential equation? If 4 moose are introduced to the new habitat, what will be the maximum number of moose the habitat can support? It doesn't matter how many I introduce, my maximum carrying capacity is 40. It's always that number there. What is the rate when the moose population is growing the greatest? Okay, so that is 20, half our carrying capacity. Well-meaning but misinformed person suggests that introducing 50 moose initially will be more moose able to hunt. Explain why this is faulty reasoning. Well, our maximum carrying capacity is 40. So you're basically going to end up killing off 10 mooses. So our maximum carrying capacity is 40. So introducing 50 will actually be harmful to our population.